This is the intro video for the IV Characteristics lab. In this lab, you're going to be studying circuit elements that do obey Ohm's law and circuit elements that do not. The power supply you're probably going to be using in this lab is the Xantrex 60-1. We also have Xantrex 60-5s, but this is probably the one you'll have on your desk. So there's a few things you need to be aware of. We're going to be using these three terminals exclusively. There's also two over here, but they put out 5 volts and ground, and you can't vary that voltage, so that's not useful to us. We do want to vary the voltage. So just use these three, ignore these two. Another thing you need to do with this Xantrex 60-1 is you need to connect a short wire between the ground terminal and the black terminal. So you just put something between them like this and leave it there for the duration of the experiment. With the other model you don't need to do that, although it doesn't actually hurt. So I'll move this other power supply out of the way for now. And now we'll talk about limiting the current that this power supply puts out. So I'll turn this guy on. The problem we have is that these multimeters that we're going to use are only rated to 400 milliamps. So that means that this guy is quite capable of burning out the fuse in these guys. So to prevent that from happening, we're going to limit the current that this power supply can put out. The way in which we do that is you start by turning the current all the way to maximum. So crank it right up to the top. Then you want to set your voltage to 12 volts. Next, you take another wire and you connect it between the positive and negative terminals. So you're putting a short right across the two terminals. And notice that as soon as you do that, the voltage goes to 0. Now we're going to adjust the current to a maximum of 0.4 amps, so 400 milliamps. Then we can remove this short wire that we put across the positive and negative terminals, and as soon as we do that, we should get back up to 12 volts. And then once you've done this, you don't touch that current knob again for the duration of the experiment. So we've limited the total current that can come out of this to a value that's going to be safe to use with our multimeters. So now we're ready to build our circuit. So here is a diagram that you've got in your lab manual for the circuit you're going to build, where Z is going to be a variety of different components that you substitute in. So you'd put in a resistor first, and then later on you'd swap it for a light bulb, and later on you swap it for an LED and a diode and a Zener diode. So this will keep changing. The rest of the circuit basically stays the same. So let's build this now. I find that it's easiest to start at the positive terminal of your power supply and just work your way sequentially around the inner loop and then add extra loops last. So let's do that now. So we go from the positive terminal of the power supply to this resistor, which is actually a decade resistor box, which looks like this. It's just a resistor that you can dial up to different resistances. So 3 times 10 ohms. So I've dialed it up to 30 ohms now. So because this is a little bit large and clunky and the terminals are actually over here, I'm just going to orient it upside down to make it a little easier to see what's going on here. So our first connection goes from the positive terminal of the power supply over to the decade resistance box. And you don't need to be careful about plus or minus with this one. The next element after the resistance is the ammeter. So we're going to be using a multimeter for this. To set this up as an ammeter, you want to use these three terminals, and in fact only 2 of them. So if you have a large current, you'd use the 10 amp scale. We're going to be working with fairly small ones, so use the milliamp scale. That means you'll hook in between this and this. So just to show you, you go from your decade resistance box over to the milliamp scale here. And then from here, we'll go to the next element, which is going to be our circuit element. So I'll put in the light bulb to begin with. So we go from the COM terminal of our ammeter over to the positive end of our circuit element. And by the way, if you're using this as an ammeter, then you'd want to turn it up to the milliamp scale there. And again, I'll just move this slightly out of the way so you can see a little better what's going on. From the component, we go next to our switch. So that's this little guy here, a tap switch. So you click it down and that completes the circuit. So again, we go from the negative end of the circuit component to the switch, and then from the switch back to the negative end of the power supply. And that's our inner circuit, and the last thing to hook up is our voltmeter. So we have another DMM here, and you want to set this one to the V with a straight line over top of it. The V with the squiggle is for alternating current, and this power supply puts out a DC current, a direct current. So we want the V with the straight line, which is that one, and we'll be using these two terminals for a voltage. So the positive end of the circuit element goes to the positive end of the voltmeter, and then the COM terminal goes to the negative end. And that's our circuit all set up. So the thing we're actually studying is, in this case, a light bulb, although you're going to be substituting other things in there. And if I push down the tap key, it lights up, so we know that the current is going through the light bulb. Now, for the 50 ohm resistor and the light bulb, you want to set your decade resistance box to 0, so you actually don't have any resistance here. For the diodes, like the LED, the diode, and the Zener diode, these guys, you have to be careful that this decade resistance box is set to 30 ohms, otherwise you will burn them out. So just be careful of that, is when you substitute these guys in here, make sure you turn up your decade resistance box to 30 ohms, or you will burn them out. So now we're on to taking data. So for the light bulb and for the 50 ohm resistor, the manual recommends that you take data from 0 to 4 volts and also from 0 to minus 4 volts. And they furthermore recommend that you go up in 0.5 volt increments for your data taking. So you don't need to be all the way at 12 volts, you're going to only go up to 4 volts. So start by going down to 0, and to take data you just press down the tap key and read the values off the DMM. And because I'm at 0 volts, you don't see very much. And by the way, never trust these values to be accurate, only get your data off of the DMMs. Because these numbers will not be terribly accurate, these ones are very accurate. So again, the manual suggests you go up by 0.5 volts. So after you've taken your data, you go up to 0.5, and you press down the tap key and take more data. And I'll just point out that especially at the low currents, you're going to find there's a lot of fluctuation in your current measurement in particular. The reason why is that the light bulb's very slowly heating up, and that can adjust its resistance. So you may need to hold down the tap key for even as much as a minute to let things stabilize in temperature. This will only happen at the very lowest currents, so it's only a few data points that are affected by this. If it doesn't ever stabilize, then just do your best for writing down an average value and adjust to a larger uncertainty to account for how much fluctuation you're seeing here. So once you've got that data point, you'd go up another 0.5 volts, take more data, and continue on all the way up to 4 volts. And then the manual says you should go from 0 to minus 4. So how do you do that? Well, you just switch these two wires. So we're going to be running the current through the same circuit in the opposite direction. So now, if I turn this up a little bit, press down the tap key, you see that I'm getting a negative voltage. So that's how you go from 0 to minus 4 volts. Now after you've taken all your data for the light bulb and for the resistor from minus 4 volts to plus 4 volts, you're going to want to swap in one of your diodes. So one of these three. I'm going to put in the LED. You do have to be careful to get these hooked up with the positive end to the positive end of the diode and the negative end to the negative end. Otherwise you will get distinct changes in the behavior you see. Also, remember that when you're working with these diodes, you must turn up your decade resistance box to 30 ohms. Otherwise you will burn out the diode. So if you've got your LED or diode hooked in correctly and you've increased your resistance to 30 ohms, then you're ready to take data with this as well. However, the manual wants you to take data between minus 10 volts and plus 10 volts rather than minus 4 to 4. So you'll go down to minus 10 volts, you'll go up to plus 10 volts. I recommend when you're taking data with these diodes, including the LED, that you start by taking data only every 1 volt, and then you graph it as you go along, because there's big sections of the graph for these devices that are pretty boring looking, And you don't actually need much data in the boring areas, that's a waste of your time, so just go up in 1 volt increments. However, then go back and fill in the data where things were getting interesting, so where you saw a change between one type of behavior and another. I'd expect you to go back and maybe take data every 0.2 volts and see what's going on in detail in here. So for the boring sections, 1 data point every volt is probably fine. For the interesting sections, go back and retroactively fill in more data to capture all the behavior there. And finally, once you've got all your data for all your circuit elements, you're going to plot the current versus the voltage for all of them. You're going to make an IV characteristic curve for each circuit element, and you're going to put all 5 curves on the same piece of graph paper. So this is something you'll pretty much have to do by hand, because you're going to be putting 5 graphs onto one piece of paper, and some of the graphs are not linear. So you put all the data on the same page, and you should draw a best fit curve through each one of them. Because the uncertainty bars are too small to really see, you can just put a little circle around each data point, rather than trying to put in uncertainty bars. Once you've got everything graphed, then you should label all the relevant quantities for each circuit element directly on the graph with uncertainties and units. Now for all experiments, and especially for this one, I strongly recommend that when you go to write up your analysis for the experiment, you go back and reread the objective for the experiment. Because this experiment in particular has a lot of stuff in the objective, and if you just try to write your analysis based on what you saw in the procedure section, you're probably going to lose a lot of marks. So you go back to the objective and you read that, and it says you're going to determine the IV characteristic curves of common circuit elements, so that's basically the graph you just made. Determine which of these elements obeys Ohm's law. That's something you can determine by looking at your graph. Describe qualitatively how the resistance of each element changes over the voltage ranges measured. And the final one is probably the most important. Determine quantities that characterize each element, for example, resistance, forward voltage drop, reverse breakdown voltages, etc. So there's quite a bit of stuff you need to do to satisfy the objective of this experiment, and you might even need to go and do some research to learn what sort of quantities do characterize each of these circuit elements and what you should be writing down on your graph. So for all experiments, and especially for this one, always go back and reread your objective before you write up your discussion in your lab report.